Bismillahirrahmanirrahim. Nahmadu wa nasalli ala rasulihil kareem. So we continue with our analysis of the Beta-Binomial distribution theory. We observe a random variable x which is binomial with n trials and success probability p. This is a shorthand for saying something which is fairly long and complicated, and which we have discussed in great detail about how you take a sample. Each sample is a individual random Bernoulli trial, each of which has a success probability. Then you add the number of successes, you get x. Basically, human beings can only think simple thoughts. We don't have very powerful brains. So the ability to think complicated thoughts depends on making summaries in such a way that very complex ideas are compacted into simple formulas and models. And so this is how, and when you want to learn things, you have to learn basic units, and then you build on top of them, and then you build higher, and that is how you get to advanced levels of thinking. So you have to create basic thoughts and concepts, and then you have to create higher level thoughts and concepts, and then further higher. And there is many stages. So now, given x is binomial and p, this simple symbol summarizes a lot of even more simple concepts. And now, crucial thing is that this is a random variable pre-experimentally. Remember that, I will keep reminding you that post-experimentally x becomes a number. There is no distribution after the experiment. So we observe a particular value of x, we do this experiment, and it comes out 40 out of a sample of 75. So this is, you can think about it simultaneously as a binomial random variable with this abstract distribution, and at the same time as a sample of 75 voters taken from a population in which 40 people have shown up to be voting for Nawaz Sharif. This simultaneous thinking of a particular and a special case, and also the general theory, is very important to be able to understand what is going on. So you have to keep thinking in terms of very particular ideas, and at the same time in the general way. So here I am talking about the general theory, but also simultaneously about the special theory. This helps you keep focused, that what does this abstract concept really mean? And unless you do that, you will get lost in the abstraction and not understand how it translates to reality. Alright, so this is the basic setup, and we're just reviewing that. Okay, so we have this x which is binomial np. The goal is to find out what is this p. We started with this p, and we have the conditional distribution of x given the data, and now we observe a particular value. And so there is no satisfactory answer. This is one very important thing to understand, that we don't know the answer to this question. To say that somebody knows the answer to this question is wrong. Everybody is just guessing. This is what the Quran says, that when we make theories and we write fancy formulas, it's all just guesses. There is no final answer to this. This is not a solved question. This is a ongoing research, and there is actually we know quite a lot. We know that you cannot find out the answer, but you can make some fairly good guesses. So the question is, how do we make these guesses? So classical inference is one method of making guesses about p, and it says that first we estimate p, and we will discuss how we estimate p later, but the basic estimate is the x over n, the sample proportion. And this is also very important, that the sample proportion, p is the parameter which is unknown, and p hat is the estimator which comes from the sample. And basically the success probability p is the proportion in the population that is a true fixed constant number, then there are three ways in which P is being used here. It's important to keep them separate. The second is that when we draw this random sample X, then there is this P which is an abstraction. It is a concept in the ideal world, in the Plato's world of ideals, that when you pick a random person from this population, there is a chance P that you will select the Nawaz Sharif voter, and there is a chance 1 minus P that you will not. Now this is an abstraction. It exists only in the imagination, doesn't exist in the reality, because this whole experiment is something which is an abstraction. It is because what we are saying is that we are choosing this person, but we had an equal chance of choosing anybody else. Now this is an imaginary thing. This is not something which is real, which is observable. And so this first P, this is a fixed concrete number which anybody can calculate. The second P is an imaginary. It depends on how you do the experiment, you see. If I tell the people that I am doing this and I do something else, then this P will not be the true P, but people will think. So this is P which nobody knows, and people can be deceived about and can make mistakes about. So it's not like the P in the population. That's a fixed number which anybody can go out and count. Now, so this X is pre-experimental. We conduct an experiment, and how we conduct the experiment will determine crucially whether this binomial distribution is true or not. But at the end of the experiment, we will have one person. Now the whole P has disappeared, the binomial distribution has disappeared. This is just one person, which is our Bernoulli trial. Then we collect 40 of these Bernoulli trials, and now out of the sample of 75, now in the sample, in the random sample, we have 40 voters for Nawaz Sharif, and out of a total population of 75. Now this is the sample proportion. This is again an observable. This sample proportion, which is P hat, which is 40 over 75, which is 53%, this is an estimate of the P. So this is the post-experimental analog of the probability P. This is the something of maximal importance, the understanding of pre-experimental theoretical abstraction and the post-experimental counterpart. There is something you can see and there is something you can hidden, and the two have rough match but not close match. And so understanding what is the pre-experimental and what is the matching post-experimental and how much they match, these are the calculations that probability and statistics is all about.
So P hat is post-experimental?
Yes. P hat is post-experimental. Exactly. So now we have 40 over 75, that's P hat, that's 53.33%. This is P hat can always be calculated. P can, in normal situations, you will not be able to calculate because it is unknown. But anyway. So now the standard error of P hat, we have already shown, is square root of P times 1 minus P over square root of n. And now I have done something without mention, which is that the correct standard error is P times 1 minus P, but I have done the bootstrapping, which is to replace P by its estimate without mention. And this is something which is again confusing. This is often done by most people, but here we are doing it this is not the correct standard error. This is an approximation to the standard error based on the bootstrap. This is all we can do because we don't know the P. So it comes out to 0.287. So a 95% confidence interval for P is that P minus P hat. Now we use the central limit theorem here, that the P hat is pre-experimentally normally distributed with mean P and standard error equal to square root of P times 1 minus P over the square root of n. So according to that, then the difference between the observation and the mean of the observation is less than 2 standard errors with 95% probability. So P minus P hat is less than 2 times 2.87%, which is 5.75%. So a 95% confidence interval for P is that P hat minus P should be less than or equal to 5.75%. And so since the P hat is 53.33%, so I can subtract 5.75 and add it to get the confidence interval, which is this 47.58% is less than P is less than 59.0.8%. This is a 95% confidence interval for the true value P. So this is the whole of the classical inference about P. Of course, instead of T2, I can use 2.6 to get a 99% interval, and I can use 1.6 to get a 90% confidence interval, and I can get other confidence intervals also if I like. So all of this is based on the normal distribution theory. This is based on the pivotal statistic, which gives us a pivotal statistic which has a known distribution, even though P is unknown. That's what allows us to do these calculations, do these tricks. So now, this is the classical inference. There are 2 flaws in this inference. One is that although we are calling it a 95% confidence interval, and people think that this is a probability statement, we are saying something about what is the probability, but this cannot be a probability statement because P is a fixed number. It is 62%, for example. So either it is within these bounds or it is not. There is no question of probability here. So now the issue is, what is this 95%? So it is a state of the mind. This is what a subjective probability is. It tells me about how much confidence should I have that P is within these bounds, given that I don't know P, even though P itself is known. So I can say that this statement is true with probability 95% according to my information. This is also important. This is according to this information. Somebody else might have more information or different type of information. He will have a different probability. This is not an objective invariant confidence interval. If somebody knows a lot more about what is going on in the population, he might reject this, that this is wrong. I know what P is and I know it's not within this interval. So you've gotten a sample wrong or something. So anyway, so this 95% is not an objective probability which can be given to everybody, that this is something you can work with. This is my subjective probability based on the information that I have. So the confidence interval is not a probability statement because it's either true or false. The second flaw in this statement is that we have used bootstrapping. These numbers 47.5 and 59.1 are just approximations based on the assumption that P hat equals P, which is a strange assumption because if I know P hat equals P, then I don't need to do any confidence interval. That's why it's called bootstrapping, because we are using something which is unknown, pretending it is known, and then finding out how much errors there is in it. Now, the way to see that this is not such a serious assumption is to change the value of P hat and see how the interval changes. So if you move P hat from 53% to 60%, you will see that there is only a small amount of difference. You can do the calculations. So the approximation is not a very serious one. But one thing that follows from that is that you should not write, as I have done, 47.58% because we don't have that much accuracy. We don't know the second decimal place of this confidence interval. So we can say maybe it's 47.5 to 59.1. Even the first decimal place is not really precise enough. So, okay. Now, before I go on, I would like to just review some calculations that we have used already because these are some important parts of theory. There is a huge amount of theory which you have been taught in your various courses, about probability and statistics. Of this, a very little piece is important and useful and used quite often, and most of it is just junk. And so I'm focusing on those things which are important. So standard error and variance, and knowing how to calculate these are and understanding what they are very important concepts. So I'll just review some very simple things. Remember, first of all, that variance and standard error are both pre-experimental concepts, and standard deviation is a post-experimental concept. Standard deviation is the analog, post-experimental analog of standard error. So standard error is calculated by looking at all of the potential outcomes, taking the difference from the mean, squaring that, multiplying by the probability of the outcome, and adding. The post-experimentally, the standard deviation is exactly the same, but instead of using the potential outcomes, the things which could have happened, it looks at the actual outcomes, and then it subtracts from the actual mean instead of the theoretical mean, and then it subtracts from the actual observed proportion instead of the true probability, and then you get the standard deviation. So standard deviation and standard error are matched. One is pre-experimental, one is post-experimental. The post-experimental standard deviation is an approximation for the pre-experimental standard error. Okay, so now we are doing the pre-experimental calculations, and I want to show how we get the standard error, which I have used already, and also some properties of standard error and variance which we use. So we go back to the Bernoullis. Remember that the binomial random variable x can be written as the sum of the Bernoullis. This is very important in deriving its properties. Any other way is very difficult, although it can be done in many other ways. So the expected value of Bernoulli is very simple. It's 1 times p, 0 times 1 minus p is equal to p. The variance of a Bernoulli is variance of bi is again the two outcomes. But the outcome this time is not 1, it's 1 minus p squared, because that's the definition of the variance. Subtract the mean and square. So 1 minus p squared is one outcome, and the probability of that outcome is p. 0 minus p squared is the other outcome, and the probability of that outcome is 1 minus p. If we add those things, we get p times 1 minus p. And I have written here in my notes that make sure you understand this calculation, and if you don't, and you are too embarrassed to ask me, ask somebody else. But this is very important to understand. Okay, so now if we have x equals b1 plus b2 up to bn, then the variance of x is the variance of the sum. This is very important, that the variance of a sum is the sum of the variance for independent variables. It's not true for dependent variables. So now for each of the bi, the variance is p times 1 minus p, and there are n terms, so we get variance of x is n times p times 1 minus p. So the variance of x increases linearly with n. As n, the sample size increases, the variance keeps increasing. This is because, well, sums के variance increase करते हैं. Now the standard error of x is the square root of the variance by definition. So it's np1 minus p, so the standard error is n square root of np minus p. Now variance has two important properties. One of them is that the variance of x plus a constant is the same as the variance of x. So now you have to understand this on two levels. On the intuitive level, the variance of x measures how much fluctuation there is in x. So if you add a constant, it doesn't change the fluctuation. But also you have to simultaneously understand it on the mathematical level. What is happening in the mathematics which allows this to happen? Well, we are taking the outcome and we're subtracting the mean. So now the x plus c is a shifted variable. So the outcomes are going to shift. They are all going to move up by c, but also the mean is going to shift. And so when you subtract, the c in the outcome is going to cancel with the c in the mean, and so you'll have the same thing as you did when you started with. And this is actually what comes out in the mathematics. So this is the intuition for the mathematics. Okay, so that's just one rule which is not relevant here, but important since we are reviewing the properties. Now the second rule is the variance of a constant times x is a squared. Variance of ax is equal to a squared times the variance of x. So again, this is quite simple. We have terms, and the variance is a sum. It's probability times the squared deviation from the mean. Now in the squared deviation from the mean, the outcome has been multiplied by a, the mean also gets multiplied by a. So when you square the deviation, you get a squared term, and this a squared term is present in every single term in the sum, so it can be factored out. So you get an a squared, which is a common factor, which comes out of the sum, and so variance of ax is equal to a squared times the variance of x. This means immediately that the standard error of ax is equal to a times the standard error of x, where it's the absolute value of a. Yani, when you take the standard error of any random variable, multiply it by a constant, whether it's negative or positive, the constant will come out with an absolute sign. So, okay. So now with these two rules, now we come back to the calculations. Now p hat is x divided by n. So the variance of p hat will be 1 over n squared times the variance of n. So the variance of x was np1 minus p divided by n squared, and you get p times 1 minus p divided by n, because there are two powers of n. And so it follows that the standard error of p is just the square root of this, which is exactly what we computed before, square root of p times 1 minus p divided by the square root of n. Another way to get the same result is to say that the standard error of ax is equal to a times the standard error of x. Now the standard of x is, we have already calculated, is square root of p times np1 minus p, and we are multiplying by a factor of 1 over n. So if we take square root of np1 minus p and divide by n, we will get the square root of n again in the denominator. Different calculation, same result. Alright, so this is just a short review of key concepts with mean variances and standard errors that we need all the time. Now we come back to the main topic for this lecture, and that is now the Bayesian inference. Now, how do we do Bayesian inference? Now, Bayesian inference is a different way of thinking about the problem. In the classical, we don't think directly about P, but we end up making a confidence statement about P. Now, the Bayesian says that let's start by thinking about P and thinking about our knowledge of P. And so now the first step in the Bayesian procedure is to create a model for our uncertainty, our lack of knowledge about P. And they say that, okay, let's put a probability distribution on P which represents our knowledge about P. So that is called the prior distribution. The prior distribution tells us, for example, a simple prior distribution could be that P equals any of the values from 0, 0.1, 0.2, or just 0.1, 0.2, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. There are 9 such values, and I give them all 1/9 probability. So this is this distribution doesn't have any objective reality. It only exists in my mind. It is my characterization of my belief about P. I think that P could be 10% with the 1/9 probability, or it could be 20% with 1/9 probability. And this is just a way of writing down precisely what my beliefs are. And usually my beliefs will not be that sharp, but I need to, the Bayesian calculation demands from me that I specify precisely what the beliefs are. Now the Bayesian argument says that every rational person has these beliefs. This Bayesian argument is wrong, but it doesn't matter. We can play this game, understanding that this argument is wrong, but we can still put a prior just to play the game. Okay, suppose that there is a person whose knowledge about P is like this, and then what will this person learn about P after observing X? So this is the basic Bayesian calculation. There is a prior distribution which represents your knowledge about P pre-experimentally. Then you carry out the experiment, you observe X. This gives you more information. Now, on the basis of this information, what is your state of knowledge about P? So this is called the updating rule, and this Bayesian formula is also called an updating formula, in the sense that you start with the prior, then you update it to the posterior. Prior means before, and posterior means after. So there is a famous joke about the Bayesian, that how do you tell a Bayesian? How do you find out who is a Bayesian? You look at his posterior, because the posterior has another meaning in English as well. So if it keeps changing, then you can see that this is a Bayesian. So now, what we are going to do is we are going to assume that P has a beta distribution, and so the beta distribution is written here. It is gamma of A plus B, which is actually A plus B minus 1 factorial over A minus 1 factorial B minus 1 factorial, and then it's P to the X. Oops, I have written this wrong. This is not X and N minus X here. This should be A minus 1 and B minus 1 in the density here. Okay, so this is the prior density for P. So this is the state of knowledge about P that I have before doing the experiment. Before taking the sample, this is what I think, this is what I believe about P. To be very specific, this is a class of priors. It depends on A and B. And for example, if I set A equals to 1 and B equals to 1, then this becomes a uniform density. So that means that all values of P are equally likely, in my opinion, beforehand. Now, actually, what the Bayesian says is that this is usually not going to be true. In this particular situation, for example, I would know that if P is the Nawaz Sharif supporters, then I would know that P is not 0. I would be quite sure that P is above 20%, and I would be quite sure that it is less than 70%. So I should construct a prior distribution which is matching to my prior knowledge, and that is actually a very important observation, and the Bayesian methods give you a superior technique to classical information when you have genuine prior information that you can use, which is not true in the classical procedures. You cannot easily incorporate prior information like you can in Bayesian. So this is a very valuable use of Bayesian techniques, which is not done very often, because it involves combining real world information with theoretical, and this is something which as a whole this theory is very weak in statistical theory, because they isolate the real world concerns from the theory. So in the book you will never find this kind of calculation, but it is very important and very useful in real world. Now actually this A and B are called hyperparameters. Just like you see the distribution X has the parameter P, X has the data distribution is binomial NP. N is also a hyperparameter. Usually it's the size of the population is fixed, but it can also be thought of as a parameter. And P is also a parameter. Now when we, in the Bayesian calculation, when we assign a prior density to P, this is the beta AB, And of course it can be any other density. There can be many others, but the beta is one which is computationally convenient. It allows the Bayesian calculations to be done easily. So now the A and the B are called hyperparameters. They are the parameters of the prior density. And actually you can have multiple stage priors, and we will deal with such models. So then A and B are the parameters of the prior density. They can also have deeper priors, and then you will have hyperparameters. So now the question is, these A and B, these are just numbers which at this point we should choose them to match our information about P. So for example, if I'm completely ignorant about P and all values of P are equally likely, then A equals 1 and B equals 1 would be good choices. If I have some particular idea that, for example, the Nawaz Sharif voters are around 40% plus or minus 20%, then I can choose values of A and B which will reflect this. They will have more probability in the range between 20% and 60% and very little outside of those numbers. So I will try to choose A and B to match my prior information. So what I'm arguing here is that, you see, X carries some information about P. And actually there is some calculations we will do later on which assess how much information there is in X about P. And so when we learn the value of X, X is indirectly related to P. You see, in fact, X over N is the post-experimental analog of the pre-experimental quantity P. So it reflects P, but how well it reflects it, this is not clear. So, but anyway, the thing is that the observation X reveals some information about P. So now, after observing X in the post-experimental situation, how should I update my beliefs? So basically, the posterior distribution is the Bayesian answer to this question. And the posterior information combines the prior information with the data information. So now, the updating formula is done by the Bayesian formula. And that's the key Bayesian calculation, which we will now do. So we start with the joint density of X and P. Now this thing is only defined in the Bayesian world, because there is in the classical world, P does not have a distribution, so P is not a random variable, so there is no joint distribution. And even now, this is a funny joint distribution, because P is a random variable in our imagination and X is a real world random variable. So I am now taking a joint density over a imaginary variable and a real world, and this can be done by lifting the data distribution up into the imaginary world, and that is how it should be done. That is, the data distribution is also an imaginary concept. It exists in the world of the imagination, and the prior distribution is also an imaginary concept. So now both those things are matched, and now so we can consider the joint distribution. So the joint distribution can be factored as conditional distribution times the marginal distribution. This is the basic Bayesian formula which we discussed in a very simple form earlier. So joint distribution of X and P is the conditional distribution of X given P and times the marginal distribution of P. Now the thing is that the conditional distribution of X given P is called the data density. This is the standard density which is this common between the classical analysis and the Bayesian analysis. The second part, the marginal distribution of P, doesn't exist in the classical analysis and is set equal to the prior distribution of P in the Bayesian analysis. So now I have written down both of those distributions. The data density, the conditional density of X given P is n choose X, P to the X, 1 minus P to the n minus X. Here there is a subtlety which people usually miss, and it's confusing, and it's just that when we look at the X, the capital X is the random variable. It refers to the whole experiment, and the lowercase x is an outcome of that experiment. The density is a function of the outcome. It is not a function of the random variable. So the density is n given n choose x, which is some particular outcome. For each outcome, the probability is different. P to the x1 minus p to the n minus x. And then we multiply it by the marginal density of p, which is just the beta density, which we have already seen. So the product of these two densities is the joint density of x and p. Now the Bayesian formula is basically to say that we can factorize it in the other way also. The other way is the unnatural way, which is the p given x, because x happens after p, so the reverse condition doesn't make sense, but it makes sense as a thought experiment, as an idea about what I know about p given that I have learned the value of x. So just naturally the joint density is conditional x given p times the marginal of p, or it's the conditional of p given x times the marginal of x. So basically finding, and these are the two functions that you need to do the Bayesian calculation. So basically the Bayesian calculation involves refactorization. You start with this term, which is cx given p times mp, rearrange terms to get the marginal of x and c of p given x. That's all that you need to do. You have to recognize which are the terms which are part of the posterior density of p given x, and which are the terms which are the part of the marginal density of x. And it's relatively easy to do that. So is this understood? This is the crucial thing, the heart of the thing. And it's very simple, but
given x,
there are two different conditional probabilities. There's the conditional probability of x given p, that is the data density. The conditional density of p given x, that's the posterior density. X given p tells you, if I know p, what is going to be the distribution of x. And p given x tells you that once I have learned the data, what is my information about p. These are entirely different things. And basically, either conditional density can be used as one of the factors of the joint, but then you have to multiply by the marginal. Okay, so now I'm going to show you how we calculate the posterior of p given x and how we calculate the marginal of x. So the first step in doing this calculation is to isolate the terms involving p and the x, because those are going to be the basic. So what I do is I rearrange the terms. I gather all of the terms which involve the p. So there are terms with p in the conditional density of x given p, and there are terms with p in the marginal of p, and I gather them all, and that's in the second term. All of these terms which have p must belong to the conditional distribution of p given x. And all of the other terms can be put temporarily into the marginal density of x. So now I have these two factors. There's the factor which has all of the terms of the p is just p to the a plus x minus 1 times 1 minus p to the b plus n minus x minus 1. This is called the kernel of the density, because it has all of the factors which involve p. The only thing that is missing from this is a constant which will make it integrate to 1. That is all. Every function of p is already automatically in here. Now to complete this calculation, I need to throw in a constant of integration here. Let's say k. I put in a k here that will make this part integrate to 1. And in order to compensate for that, k, I need to put in a 1 over k here, and that's it. If that's how you do the complete calculation. If I could put in a k here which will make that part integrate to 1, then it is guaranteed to be the conditional density of p given x, and the other part, whatever is left over, is automatically the marginal density of x. So there's only one step to doing this calculation, and that is, first we isolate the factors of p, then we find what makes those factors of p integrate to 1. And that's all. And then we are done with the Bayesian calculation. So here's what we need to do. I want to find a k such that the integral of k multiplied by the kernel of p equals 1. And this range of this integral is from p equals 0 to 1. So this allows us to compute k, because I can take the k out of the integral and say that 1 over k is equal to this integral. And this integral is called, by definition, the beta function. I've just copied this from the wiki because I was in a hurry. The beta function is defined as this quantity here. Beta of x and y is the integral from 0 to 1 of t to the x minus 1, 1 minus 2 to the y minus 1 dt. And that's exactly what we have here. P to the some power minus 1, 1 minus p to the another power minus 1, integrated from 0 to 1. Now, the key property of the beta function is this relationship, b of xy equals gamma of x times gamma of y over gamma of x plus y. Those people who have some skill with integration can easily verify this. It's not really a very complicated relationship. In fact, it's, the formula is given in the Wikipedia, how you derive the result. So, since that is the beta function, the integral, so the constant which is required to make it integrate to 1 is the reciprocal of this. Just 1 over k. The integral has to be, you have taken 1 over it. So basically the parameters of the beta are, on the one part it's x plus a, and on the other part it's n minus x plus b. Those are the two parameters. Why? Let's have a look. Yeah. So you see p to the a plus x minus 1, that's the a. It's no longer, the beta density, the prior density had a and b. But now the posterior density doesn't have a and b. It has x plus a instead of a, and b plus n minus x instead of b in the powers of p. And those are the things which are the new beta density that is coming out, and as the posterior. And that's really why the conjugate function does, is that it keeps the prior density in the same form but just changes the parameters. So basically that's it then. I've calculated the constant which is required to make that density integrate to 1, and so here is the Bayesian formula answer. The constant, the k that is required is gamma plus of, this is n minus x plus a plus b plus x on the top, and the minus x and the plus x cancel, so you have n plus a plus b in the numerator, and then you have gamma of x plus a and gamma of n minus x plus b in the denominator. Now this you have to match by putting in the reciprocal of this inside the marginal density of x. So these are the two factors. The first factor is the marginal density of x, and the second factor is the posterior density of x, of p given x. So basically that's the Bayesian solution to the problem of inference about p. This posterior density is what we know about p after we learn the value of x. So this is the post-experimental distribution. Pre-experimentally, p is beta with parameters a and b. Post-experimentally, b is beta again with parameters x plus a and n minus x plus b. So actually that's the virtue of the conjugate prior, that we get the posterior is the same form as the prior. So that is what makes the calculation easy. Now, so this is the Bayesian answer to the inference question. But now we go into more details. This is basically the answer to the question of it. This is our knowledge about P given x. Now we break it down into more specific answers. What is the counterpart of the estimator? You see, the classical theory tells us that the after we observe x, what should we estimate to be the value of p hat? Well, we should make it the same as the sample. So basically, the post-experimental proportion of voters for Nawaz Sharif is equal to the pre-experimental p, which is the theoretical probability of drawing a voter, which is also equal to the true percentage of voters for Nawaz Sharif in the population. So there are three different p's here. That's the point estimate. That's called a point estimator. Somebody says, what is your estimator? So the posterior density doesn't give us an estimator. It gives us a range of possible values with different probabilities. So how do we get an estimator? Well, there are actually three possible estimators that are used, and they are the mode, the mean, and the median of the posterior density. And depending on the situation, different any of the three can be suitable. But the standard Bayesian theory uses the mean of the posterior as the estimator. So let's first calculate that, then we will look at the other. So first thing is that the expected value of, so what is the mean of the posterior? All that we need to do is to calculate the expected value of a beta density. And that's very easy. Here's the calculation that's given in the Wikipedia. I didn't like it because it doesn't make clear what's going on. The calculation is correct. It's the mean is alpha over alpha plus beta. But the calculation is done like this. Again, this is something that's important. First we have the integral. ये हो गया हमारा density of P, which is the beta density, gamma A plus P over gamma A gamma B, P to the A minus 1. और expected value calculate करने के लिए you have to multiply this by P and then integrate. So what happens is that P to the A minus 1 will become P to the A plus 1 minus 1. Yani one power will be added. Now the integration is very easy because I know what makes it integrate to 1. So I put in the required values, because this is when A1 is added to the A, then this is a beta density with parameters A plus 1 and B. So I put in gamma of A plus 1 plus B at the top and gamma of A plus 1 times gamma B at the bottom, and now I know that the integral is 1. These two factors that I've put in, I take out of the integral, the reciprocal. So gamma of A plus 1B is on top, I put it on the bottom, and gamma of A plus 1 I have added at the bottom, so I put it on the top. And also the gamma of A plus B that was previously there, I factor out, and the gamma of A that was previously there, I factor out. So the 4 gamma functions outside the integral are the result, because the integral itself is just 1. And now this is gamma of A plus 1 divided by gamma of A. That's A factorial over A minus 1 factorial, and that's just A. And then it's gamma of A plus B over gamma of A plus B plus 1, And again, that's a plus b factorial in the denominator, and a plus b minus 1 factorial in the denominator. Again, that's cancelled. So you get a over a plus b. Okay, so now having done that, the Bayesian estimator of p is just x plus a over n plus a plus b. Now, a natural prior for p, which is called the ignorance prior, is suppose that you know nothing about about p, so you will set a equals 1 and b equals 1, because what that means is that all values of p are equally likely. Any other value gives preference to some values of p and gives less probability to some other values. So the natural prior is a equals 1, b equals 1. So now, with this, then our Bayesian estimator for the probability for the sample p, success probability p, is x plus 1 over n plus 2, which is somewhat different from the classical estimator. Now, when x over n are large, there is no difference between x plus 1 over n plus 2. Yani, we are talking about 1000 or even 100. So this will make 1% or 2% difference. So it's not important. But it is interesting to see what happens for small samples, because that's actually where the Bayesian estimator has its advantage. If you look at a sample of size 1, I take just one person as my sample, random sample. So if he is not voting for Nawaz Sharif, then my classical estimator says that 0% chance is the 0% is the proportion of voters, which is not very nice. And if I pick somebody who is voting for Nawaz Sharif, then I say 100%. All of the population are voting for Nawaz Sharif. Again, this is not a very nice estimator. Now, what the Bayesian estimator does is that it says, okay, let's look at x plus 1 over n plus 2. So now when x is 0, then this becomes 1 over 1 plus 2, 1/3. So it moves from 0% to 33%. That's a very reasonable estimate. Yani if you pick one person and you're going to estimate how many Nawaz Sharif beta estimators on the basis of just one sample, then 33% is your adjustment to the 0%, which is what the sample is telling you. So what the Bayesian is doing is, let's look at the other side. Now if it is 1, then the Bayesian estimator is 1 plus 1 over 1 plus 2, which is 2/3. So now what the Bayesian estimator is doing is a phenomena which is called shrinkage. Very important phenomena. The prior mean, before we know anything, is what? A is 1, B is 1, so A over A plus B is 1/2. And also, if you have the uniform prior, what is the mean of the uniform prior? 50%. So a priori, our prior mean is 50%. That because we don't know anything, so if I'm asked to guess how many voted for Nawaz Sharif, I will say 50%. Either side is equally likely. So now I observe a sample of size 1, and okay, I see that the 1% is voting for Nawaz Sharif out of a sample 1. So 100% in my sample, random sample, are voting for Nawaz Sharif. So the data distribution, the data estimator is 100%. So now I have two estimators. One is my prior information 50%, and the other is my data information 100%. So now my posterior is an average of these two quantities, but the average is not done mechanically. That would be 75%. It's done by actually you take into account the weight of evidence. How much information is being given by the data. If there's a lot of data, then the data gets more weight, and if there's little data, then it gets less weight. So that's built into the formula. So anyway, the formula says 66%. It discounts the data. It's not the data and the prior are not taken into account equally. The prior is given more weight because there is very little data, but still data is given some weight. Maybe you can say that it's given 2/3 of the weight, and two-thirds of the weight is given to the prior, and 1/3 is given, or with some combination of weights, you will get 66%. And similarly, on the other side, you get 33%. So you are showing this shrinkage phenomena. The data mean is being shrunk towards the prior mean. Now, there is another way to calculate the Bayesian estimator, and that is called the modal estimator. You look at the posterior, and instead of calculating its mean, you calculate its most likely value. Under certain types of loss functions, depending on what you're trying to do, sometimes you want to say what is the most likely value of P, instead of saying which is the average value of P across all of the possibilities that I have in mind. So this is a different question, and it has a different answer, and you can calculate. And now if you just look at the beta density, it's easy calculation, which I didn't have time to do this morning because I was very busy. But basically you have the beta density, it's P to the A minus 1 over 1 minus P to the B minus 1. You can throw away the constant because it won't affect the shape of the density. You're just trying to calculate the maximum. And so you take the derivative with respect to P, and you set that equal to 0, and you get alpha minus 1 over alpha plus beta minus 2 as the maximum value. This is true when A and B are both bigger than 1. When A and B are both less than 1, then this is the minimum value. It still has derivative 0, but the curve is now shaped like a U. When A and B are less than 1, then remember that the beta density has power A minus 1. It will go to infinity near 0. And if B is less than 1, then it will go to infinity near 1. So in both cases, then you will have the minimum value at this mode. So it's called an anti-mode in that case. So when A and B are bigger than 1, then this is the mode, A minus 1 over A plus B minus 2. So in the case of the so if you look at the modal estimate for the beta, you get exactly the same as the classical estimator. You get with the uniform density. You get n plus the first parameter is x plus a, and so it's x plus 1 minus 1. The 1 gets subtracted, and then you have n plus b and n plus 1 and n minus x plus 1. Those are the alpha and the beta, and then the 2 plus 1s cancel with the plus 2, and x cancel with x, so you get basically x over n. So this time, if you use the modal estimate, the mode of the posterior density, this is exactly matched with the prior density, with the frequentist estimate, the standard estimate, which is x over n. The classical theory of estimation, I want to compare the Bayesian estimators. There is also a median estimator which has its own theory, which I won't go into because it's not used very often, even though that is the best estimator, but for various reasons that is not the one that is currently being used. But okay, so now I want to compare the theory with the classical theory again. So the classical theory is based on the you see I've developed the confidence interval, but if the classical theorist is asked to give a point estimator, then the most standard classical point estimator is the maximum likelihood estimator. What the maximum likelihood does is that it looks at the data density, and the first step is to convert the data density into a likelihood function. This is very important because it's just a mental shift. The data density remains exactly the same as the mathematical formula. It's n choose x, p to the x, 1 minus p to the n minus x. But now the data density is a function of x. The x keeps changing, the p is fixed. Now the likelihood function is exactly the same function, but we think of it as so basically we think of it in the post-experimental situation where some particular value of x has been observed. So now the x is fixed, it's a number. And now the p is thought of as the function. So now we say that, okay, I observed a particular value of x. X is 16 or 17 or 32. Now I want to know which value of p will make this observation the most likely. I need different values of p give different probabilities to the observed outcome. Now, which is the value of p which gives the largest probability to what I saw? This is the question that is being asked. So we just maximize. So the function is p to the x, 1 minus p to the n minus x. This is exactly a beta density kernel with the x plus 1, minus 1, and b equal to n minus x plus 1. Because the beta density, okay, so let me write this down. Likelihood function for p is proportional to beta density with two parameters. The first parameter is x plus 1, and the second parameter is n minus x plus 1. So you just look at the form, and that's what the plus 1 is put in there to cancel the minus 1 in the beta density. So now I know what the mode of this is. I already calculated. Actually, and it's alpha minus 1 over alpha plus beta minus 2. So if I do that, it will just come out to x over n, because the plus 1 will cancel with the minus 1 in the numerator, and the plus 2 will cancel with the minus 2 in the numerator. So it will just be, so this is the standard p hat. So this is the p hat is the maximum likelihood estimator of p according to the classical calculation. So now the mode of the modal Bayesian estimator is the same as the maximum likelihood estimator. Alright, so I think I will stop this lecture here. The mathematical appendix gives some of the integrals. Those are not necessary, as I have said, but it's useful to have these as well. Over the course of many years, I have learned those things that are useful and those things which are not. So over the course of many years, I learned a huge amount of mathematics which I have stopped using for the past 10 years or so, because most of it is not very useful. A very little bit is useful. So I am trying to teach the parts that are useful. The integrals that integral formulas in this are not actually useful, in the sense that you don't use them in the calculations, but For the simpler ones, it's useful to go through them just to acquire the confidence that you know what is going on. Otherwise, basically, a lot of theory is learning how to use it is like learning how to drive a car, and learning the formulas is like learning how the engine works. So now these two are entirely different skills. You can be an excellent driver and have no concept of what is inside the hood. When you open up, you won't know where the radiator is, if possibly, and where the battery is, and where the spark plugs are. So you may not know anything about it, but you can be an excellent driver, because driving doesn't have to do with knowing what's in the engine. And you can be an excellent mechanic, know everything about the mathematics, and have no idea how to drive the car. So these are different skills, and normally in the courses, and if you look at all of the Bayesian textbooks that I have, and I've looked at them, they all are teaching you about the engine. And even after you read them, you will know, first of all, it's very difficult. I mean, learning about the engine is very difficult, but it will not teach you how to use the theory also. So it's doubly useless. You invest a lot of time and effort, and you get nothing in the end because you don't know how to drive the car. So I'm teaching you how to drive the car, but a little bit some pieces of the engine are also useful just to feel comfortable that if the car stops in the middle, I can open it up and I can have a little bit of look at it and see how to fix it. So only those parts which are useful I am covering in these lectures. All right, so that's all for today then.